Hi everyone, today we're going to talk about circular motion. So I have this diagram here where I have a particle, point A, which is moving around a circle. Let's imagine that it's got a velocity here of v, and as it moves around the circle in an anti-clockwise direction, we're interested in figuring a few things out about this. So we'll start off by saying that the circle has a radius of r, and that the object does one circle in a time period of t. So we could measure the angle from here. So we normally start from this point, just like with the unit circle, and we could measure the angle through which it has moved. Theta would be called the angular position. Remembering where theta equals 0 is the x-axis direction, and one full circuit would be an angle of 2 pi in radians. Now, because we're moving, we could talk about the angular velocity, how quickly the angle changes. We designate this with the Greek letter omega, and it would be the angle for a full rotation divided by the time. So it's an angular distance of 2 pi to go once all the way around, divided by t. Now we could talk about the speed as well, the tangential speed. Designate this as v. Now, how far does it travel to go once around the circle? It travels the distance 2 times pi times the radius, and then we divide by the time. That's literally distance divided by time. If we look closely, we could write this as 2 pi over t separately multiplied by r, and then I hope we can see that the 2 pi over t is omega. So there's something new and valuable. The tangential speed equals the angular speed multiplied by the radius. The angular speed would be in radians per second, and of course radians is really just a ratio, it's a dimensionless unit. So we have a distance here perhaps in meters, we have an angular speed here in per seconds, and we get a linear speed in meters per seconds. Dimensionally that is consistent, and it makes sense to have such a formula. So that's interesting. Now, if we're interested in the x and the y position of this particle, if we're interested in the vector r, so let's call this vector r, and it is a vector because it starts at the origin and it points towards the location where the particle is. That vector r has an x and a y component, and the x component, strangely enough, would be r multiplied by the cosine of theta, and the y would be r by the sine of theta, just like it always was on the unit circle. So we will write this down. The vector, the position vector r, it will depend on time, depends how fast it's moving. The x component was r by the cosine of theta by basis vector I, and then r sine theta by the basis vector j for the y component. Theta, of course, well, an angular velocity could be the angle covered divided by time. This is a variable time now, so if we've gone for a time which is half of the period, we'd have an angle which is half of a full rotation. Importantly, we could write theta as omega multiplied by t. So this is typically written as r cosine omega t by I plus r sine of omega t by j. That's the position vector r as a function of time. Now let's have a quick look at that in action. I've got a GeoGebra going in here. So the point A here, I have a variable radius. I've got it set to 5. I've got a variable time period. Let's set that to 10. And now if I start the animation for time, there it goes, following its way around. I haven't drawn the position vector. At any point, the position vector would be going from point O to point A. And it's usually designated R because, of course, it's the radius of a circle. This is uniform circular motion as the thing moves around. So we'll just leave that one there for a minute. And we'll go back to, where are we going back to? We're going back to OneNote. So that's our position vector. Now let's do something a little bit calculus-y. Let's think about the velocity of the particle at any time t. We know that that is the time derivative of the position. So we'll take a derivative of the formula we have there. So r is a constant, it'll stay. Derivative of cosine is negative sine, so I'll put the negative and I'll write sine of omega t. And then the derivative of omega t is omega, and that is the I component. Now let's do the j component. In a similar way, derivative of sine will be cosine of omega t. Derivative of that is omega, so we'll have r multiplied by omega, and that's the j component. This is our velocity vector as a function of time. So the velocity will change depending on the value of time. Sine and cosine change periodically, and so the velocity vector will point in a different direction. Now I think you can see what's going to happen here. I'm going to go back to one I prepared earlier, and I'm going to turn on the velocity vector. So at this point when time is 0, the velocity vector is pointing straight upwards. And let's just start making the time advance. Here we go. So you can see that the velocity vector isn't getting longer or shorter. The amount of the vector isn't changing, the magnitude, but the direction most certainly is changing. And remember, vectors have two important parts to vectors, magnitude as well as direction. As if the direction changes, it is a different vector. So that particle, although it's not getting faster or slower, its velocity is changing from every moment to the next. And as you know, when velocity changes, then we say that there is an acceleration occurring. All right, let's just pause that there. Put it back to where I started from. The other thing important to note is that at any point around the circle here, the velocity vector was tangent to the circle. So it's acting to change the, I don't really know what I was trying to say then. It's just tangent to the circle. Hopefully that's clear enough from the diagram. All right then. I think that video's long enough for one instalment. I'll be back soon with part 2 where we determine how quickly that velocity changes.